Hello and welcome to TidyX episode 172. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
And my name's Patrick Ward. Thanks for checking in with us at TidyX. As always, like, subscribe, drop comments on that YouTube channel. And if you enjoy the show and would like to support it, we do have a Patreon page. That said, episode 172, we've been doing our little 20 minutes of this, that, and the other thing. And today we're going to do 20-minute quick hit of logistic regression. Hopefully a concept that then we will carry forward over the next few episodes.
Yes, indeed. So we got asked by one of our viewers when we did episode 169, where we predicted Hall of Fame batters or Hall of Fame people getting into the Hall of Fame based on batting data, and we removed pitchers. We were asked then by a viewer, hey, what about pitchers? Do you want to predict if any of them will go into the Hall of Fame? Because I'm assuming there are some pitchers in the Hall of Fame. So let's go through using pitching data now. Who's in and who's out of the 2024 class? We know that this was already just done, so we can actually verify if we were correct at the end of this. So the way we start is we get our data and our data manipulation tools from Lahman and Tidyverse. And we load all that in. With Lahman, it has all this batting data, which is fantastic. We're going to then use one of them called the pitching data set here, which has a bunch of information. Rather than just printing it out, we can just bring it up here, and it's just got all this information about pitchers, such as how many shutouts they had, how many saves they had, hits, earned runs against them, number of wins they had, number of losses they had. So it's a pretty solid data set to get for free just by loading Lahman. We're going to then filter to remove any players pre 1970 for no particular reason other than trying to make sure we're not looking too far back into history. So the first thing we're going to do is we're going to say, okay, what pitchers started playing pre 1970? So we're going to filter pitching by year ID to get anybody pre 1970. Pull that player ID and say, okay, these are all the pitchers that pitched before 1970. But we want all the pitchers that started. Their rookie year was 1970. So they wouldn't have played in any data set before that, right? So we're going to say, hey, pitching, we're going to filter and remove any player IDs if they appeared before 1970. You may notice that this is exactly what we did in episode 169. So now we've got our pitchers post 1970, and we're going to now figure out which of these players are eligible for the Hall of Fame. So there are some rules around it. First is they need to have not played over the last 5 years. So we're going to remove anybody that played up until or up through 2019, right? So any max year greater than 2019, sorry, you're out. And then the other thing is they needed to have played for at least 10 seasons. So you take the maximum year that they played and the first year that they played, subtract it, and that value has to be greater than or equal to 9. And that's just because if they started playing in 1990 season and they finished playing in the 1999 season, that is technically 10 seasons. So that's why it's 9 as opposed to 10 here. So sometimes you got to think about the way that numbers work when you're doing that. So now we filter that out. Now we have our eligible pitchers, but we need to calculate some stats on them. Patrick, how do we collapse all their career stats down or year stats down to their career stats?
Yeah, so we got season data. So we're going to summarize by player ID. So we're just going to group them all, kind of clump them all together based on their player ID. And we're going to select out some rows. So we're just going to get rid of the batting average of the opponent and the ERA, just because those are averages and we don't want to take averages of averages. And I don't think we have enough data enough of the information we need in this data set, at least, to calculate on a career level those averages, the ERA and the batting average of the opponent.
Exactly. Because I think we looked it up. Earned run average is earned runs divided by innings pitched times 9. And so we don't have innings pitched in this data set, unfortunately. So we couldn't calculate that for ERA for career. And then the opponent's batting average, that would be rather calculate or difficult to calculate, I think.
Yeah. So we're going to drop those. By player ID, we're going to summarize across wins and all the way to GIDP, which was grounded into double play. And we are going to do this across. So we're going to sum each of those columns by player ID. And then we're also going to create a new variable called final season, which is the max of their year ID. And then dot groups equal drop, just drop the grouping variable. So now we have a summarized data set.
Okay, we should look at that. We've got all that information, and now every player should only have a single row, and it looks like they do. Here, caused me a little second of concern, but when I saw the G, J, and P, so unique all the way there. So you can see like this player or this pitcher had 16 wins across their career, 18 losses, and 331. Is that 331 games?
Yeah,
So they.
games.
Great. Now we're going to add in the metric that we care about is Hall of Fame. So what we're going to do is we're going to take the Hall of Fame dataset, which is included again in the Lahman package. Hall of Fame. It helps if I spell it correctly. What did I do wrong? Whatever, do that. Oh, the capital O. And it's got a bunch of fun data there where it's every player, every year they went up to be voted on, and then a bunch of metadata about them, or not metadata, a bunch of data around how many votes did they need, how many ballots did they receive, and then eventually whether they were inducted or not. But what we care about is whether they were inducted or not.
Mm-hmm.
So if we select just player ID and inducted, you see that we have either an N if they didn't, or yeah, if they didn't get in, if they were not voted in, or a Y if they were. So we can do select by player ID and inducted, group by that player ID, and then go, hey, if there's a Y for that player, that means they got in. So just as long as there's a Y, they were inducted. So sum of Y is greater than 0. That way, if a player went up 10 times and was voted no 10 times, this will return a 0. So we end up now with this Hall of Fame data set there that has Booleans. So Aaron HA01 was inducted, but Abbott was not. And we just thankfully can use one of these handy dandy left join functions here, which is going to take this data set that we have, their career eligible pitchers with their career stats, and we're going to left join. So sock it on to the left, add it on to the data set there by the player ID. So it'll match it based on player ID. So now we have this data set that has all this information about their career. And then finally, in the last column, if we have information about whether they were inducted or not added to it. So now if we want to identify the players that are or pitchers that are available for this year, all we have to do, so in theory, they should not have any values in for inducted yet. So we can take this and filter by final season is 2018. And let's take a quick head of that guy. Actually, I wanted to select player ID and then just inducted. Because we should get, yes, a bunch of NAs because they have not been voted for yet. They are not in the Hall of Fame data set. But we've got also a couple other groups of players that we've got to deal with. First are people that have been eligible and therefore may or may not have had votes for them. So we'll take that, we'll filter to keep any season pre-2018, and then we're going to mutate the inducted column because some of them may have NAs because they were never voted for, right? So that they wouldn't be in the Hall of Fame data set. So we're going to say, okay, if they were never inducted, or never voted for, so they're not in the Hall of Fame data set, and if their final season was pre-2009, so now they are no longer eligible to be voted into the Hall of Fame, we're going to just drop in a false there for our data set purposes. And then if they don't have an NA value, we're going to keep the value there. So now we've kind of ended up with anybody pre 2009 now has a false if they were never voted in because they can never be voted in. But anybody before that will still have NAs because there's the potential for them to be voted in technically. But now we've got people that are it's final. They don't have any more chances to go to the Hall of Fame. And so let's drop those into a data set that we will then train our model on. And then we have players that have not been voted in, but they're still technically eligible. So we want to leave them in another data set. So we're going to end up with three: the 2018, the folks that are new, the folks that still are hopeful to get into the Hall of Fame, and the people that they either did get in or, sorry, they're never getting in. So we take this data set here, we filter to keep any cases where it is inducted as not NA, and then we filter to keep their final season is greater than 2009 or they were inducted. So this is important because they could have been inducted, but their final season was 2012. So this keeps them in this data set. And then finally, this is anybody that is after 2009 and either has inducted as false or is NA, which will now keep everybody that is TBD. So let's take a quick peek at this data set here. So this is all the people that have final results. So like this person was not inducted and their final season was 1990. So they are no longer eligible to go in. I guess all these top people here on the top of this data set were all false, so that none of them got in. So I think let's take a quick peek at this out of curiosity. How many people were eligible? How many people did get in? How many pitchers in our final data set? So only 15. So this is something to keep in mind where we had 568 potential pitchers and only 15 of them got in. It's a rare event, apparently. I don't make the rules. I'm not a voter.
Yeah.
But this is something to keep in mind when you build your model. Patrick, how are we going to build our model?
We're just going to build a logistic regression here to start. The first model is going to be all the variables, which is a bit silly because so many of them are correlated with each other highly. A number of them don't mean anything. We run that model. We get a warning. The fitted probabilities are all numerically 0 or 1. The model, the algorithm did not converge. When we click summary of this model, so we're going to see that obviously everything looks really weird. Like the Z values are all zeros or negative 001s. The standard errors are massive. The p-values look all weird. They're either 1 or 99. So this is not a good model. It's not a good thing to do. We fit all those variables. That was not a very great idea. So let's make a much more simple model, just kind of a little domain expertise would indicate that innings pitched, that's like innings pitched per outs or something like that, per 3 innings or something like that. I can't remember what IPOTS is.
Let's bring up the data set.
Uh,
Pitching the IP outs pitched.
Outs pitched, innings pitched times 3. Okay, so outs pitched plus strikeouts plus runs. We'll just build a simple model with that where we're trying to predict the binary outcome of inducted or not true or false. So now if we had a summary here, obviously we didn't get that warning. Things look a little bit more normal. So just kind of like interpreting these, remember the coefficients are all on the log odds scale, but outs pitched is positive, suggesting that for every outs pitched innings, every unit increase, we see a positive increase in the probability of making the Hall or the log odds of making the Hall. Same with strikeouts. So for every strikeout, when unit increase in strikeout, we see a increase, positive increase in the log odds of making the Hall. And then for runs conceded, obviously, that goes the other way. So that suggests that we see a decrease in the log odds of making the Hall. Again, these are on log odds. So if we exponentiate them, we can get them back to a nice scale that is regular odds. So for example, innings pitched, we would say that for every 1 unit increase in innings pitched, we are increasing the odds of making the Hall, at least on a relative scale, of to 1.003. So 1.003 times. Same with strikeouts, it's positive, and then runs is a decrease in odds of 0.98, or really a decrease in odds of on a relative scale 2%, 1 minus 0.98. So that's a little bit of what the model's saying. We can, of course, take this model and use it to then predict on the in-sample data. So we're going to predict it on the in-sample data set. We use type response because we don't want, because we do want the outcome variable, or the predicted variable rather, to be on a probability scale. If we don't use that, it's going to give us on log odds scale, and we have to take the inverse logit. And it's Saturday morning; we don't feel like doing math, so
Math is hard. Okay, let's
we
just
don't want to write
quickly.
don't feel like writing a function for that. So
Yeah, let's quickly look at what the data looks like here. Deducted and then preds. Players? No. What's the column? Why do I not here? No, not head. We want select here.
Yeah.
There we go. And I was right there. There we go.
Yeah. So there we have
quick
our
logic check.
Yeah. So we have some probabilities. So like, for example, the first guy had a probability of basically 0.8% of making the Hall of Fame, and he did not make the Hall of Fame. We could look at some of the people that were true.
Live coding.
Right. So these guys had very high probabilities of making the Hall.
Well, this one person did, according to our model.
Well, high probabilities relative. Remember, there's only
That's
15
true.
guys. So, and that's something to keep in mind. The default that people always use is 50%. Anything over 50% gets a 1, gets a yes or a no, or a true or false, which is kind of silly. Logistic regression, I know it gets taught as a classification model, but it's not a classification model. It's a regression model. It is giving us probabilistic outcomes. So we can interpret these as probabilities, and we have to keep in mind those probabilities relative to the base rate of getting into the Hall of Fame, right? Relative to the prevalence of getting into the Hall of Fame in our data set, which was whatever, 15 divided by 568, or I think it was 568. So like 3%
Like
guys, 2.5% or something like that are going to get in. So, and so if we actually pull out all 15 of the guys, can we just do that same thing up that you just did there, but just get all 15 of them?
Good memory too, by the way. 568. Bravo.
There we go. Yeah. So maybe just do print n equals 15. And let's just see them all. So can we arrange them by
Yes.
descending? Let's see what the lowest guy had. Right.
164.
So the lowest guy had about 164%. So by contrast, do the same thing just with the head of the false, and arrange them as well by descending, and let's see what the highest false had, right? So the highest false.
Oh, I should have that print in there.
Oh,
that was
yeah,
dumb of me.
something looks weird. Okay, yeah, there we go. So the highest false player had a 0.8%. So even our lowest true guy was lower than the population prevalence of 2.5%.
Oh, no, the model.
Sorry, there we go.
Yeah.
So
I had it doing like weird backwards
this
things.
is great. So look at these guys. So that's Roger Clemens. So steroid era, 99. You would say based on his statistics, he's a lock.
Gotta get in.
But the writers don't want to vote for him. Kurt Schilling, kind of like I think to the media perennially a jerk, so they don't want to vote for him. But he has the stats to be in the Hall of Fame. The
According
other
to our
thing,
model of three different things, three
yeah,
different
right.
predictors.
Three different things. The other guys I can't. David Cohn, I see there at number 6. The other guys I don't really recognize the abbreviated name player IDs. That's
It's
okay. Anyway,
like player info. Is it player info? No.
I don't know, but anyway, that point being, that is pretty cool. Like to see that if we were basing this on stats alone, some of these, the 3 stats that we use, when we can use more, and we'll extend this anyway. Let's move on. But
Yeah.
it's fun to look at to look at the outputs of the model. So the other thing we can do here, the last thing that we're going to do, and then we're going to move on and save other stuff for next week. But the last thing we can do is produce a calibration plot. So calibration describes the agreement between our predicted and our observed or our actual outcomes. And so the way that we do that with a binary variable is we put the predictions on the x-axis, and we put the numeric outcome of a 1 or a 0, the Boolean, true or false, because it's true or false, we use as numeric. We put that on the y-axis, and we draw a smooth regression line, and we draw an AB line, so which would be a line of perfect predictions. If our model is perfect, the smooth line will lie directly on top of it. And our model is not perfect. It's not well calibrated, obviously, because we see that there's some guys there that have like 99% and they never made it. So what this is telling us is, for example, it's saying, let's take predicted 50%. It's saying every time the model predicted 50%, the true percentage of people that had a 50% prediction that actually made it to the Hall was probably somewhere actually around maybe like 35 or 40% or something like that. And you can see, because of our smooth line is below the line of expectation, below a line that has a slope of 1 and an intercept of 0, our model is consistently under predicting. And this is really how regression works. Regression is pulling things down towards the mean. And our mean was that there's only 2.5 or 2.6% of the people that actually make the Hall. So it's never really overly bullish on some, and then the few guys that it is overly bullish on, maybe like Schilling and and Roger Clemens, they're not getting voted in because votes matter, not just
Mm-hmm.
stats.
It's not just pure. This person should get in because they were the best.
Yeah, so
I
we
mean,
would
it
say
should
this model
maybe.
is not well calibrated, and we'll go into future things on discrimination and checking the model and evaluating the model. But
So it's not that it's a bad model; it's just poorly calibrated.
so not a well calibrated model, but interesting and fun to play with. And that is a little bit about just the basics of logistic regression in R.
Yeah. Thank you all so much for joining us. We got this in roughly 20 minutes, so hopefully you'll forgive us. And with that, thank you for joining us. As always, my name is Ellis Hughes. You can find me on social media sites at Ellis_Hughes.
My name's Patrick Ward. You can find me on X at OSPPatrick, at Tidy_Explained is where the screencast lives on X. As always, though, the YouTube channel, easiest way to get in touch with us, like, subscribe, drop comments down below, questions, etc. And if you enjoy the show and you'd like to contribute, we do have a Patreon page. The link is accessible in the comments or in the notes section, rather,
Yes.
of this YouTube video. So if you'd like to donate, we are grateful for that.
Thank you all so much. Keep on exploring your world.